for the book because mine seems to be corrupt. So we call these guys SCRs for short, silicon control rectifiers. These are very, very important. These, like I said, these are primarily used. We use them for different things, but their primary use is in DC motor drives, variable speed motor drives. So, no, you're thinking about AC drives. We're talking about DC drives. So SCRs are the main control element used in variable speed DC drives. This is what they are. This is the way they're made. So we call these things thyristors. So it means they have 3 junctions. The junctions are called the anode and the cathode. Where do we pick up that from? And then we have a thirdly that we call the gate. So what you notice is that the symbol for an SCR is pretty similar to the symbol for a diode. Except so this right here is the anode, the arrowhead is the anode, the bar is the watt, the cathode, and this guy here coming into the side, this is the gate. But it is not a diode. So to set this thing up to work, we have to make the anode positive in respect to the cathode. Don't have much room. I'll try to show it before we can have an attempt to turn it on. But the way the thing works is you forward bias it, it's not on until you trigger it on. So what we can do is we can do what with this guy? We can control when it's on. But to turn it on, it's got to be forward biased. If you reverse bias it, it's going to do what? It's going to turn off. No, it's not going to break over. It's going to break over if you exceed the breakover voltage, right? You understand? So it's not going to break over. It's going to turn off. And of course, we're going to make sure that we don't exceed the breakover voltages or we can damage the device. We can still force current through it, right? You understand. But if we operate it within its parameters and don't exceed its breakover voltage, then if I don't have this thing, when it's reverse bias, it turns off. When it's forward biased, you have to turn it on. Now, this is the makeup right here. It's got 3 junctions. So if I come over here and put a positive right there and a negative right there, is there any 2 junctions that are forward biased? So up here I have a P, but that P runs into an N. And there's no N on the N yet, right? You understand? Down here I have a negative I have a negative potential relative to the anode. Now this gets confused. I try to iterate that this is not going to be negative and that's not going to be positive, right? It's going to be relative to it. So the cathode would be negative in respect to the anode. So this negative would forward bias this, and it would start pushing electrons toward that, but there's nothing on the other side to pull them out, right? You understand? So that guy would sit there, and it would be just like it was turned off. What do you think we got to do with the gate? It's got a what? It's a what? It's a P. So what do we need to do with the gate? Well, if I come over here and do this right, and I put a little old tiny P on there, then this junction forward biases. This is a big positive. This is way down here, right? You understand that? So here comes these electrons come flying up here. A few of them go that way, but now this negative moves to where? Moves right there. Now this junction right here is forward biased because this bottom diode is only dropping about 0.7 of a volt. So now this guy right here turns on. And now you have the things turned on. What would happen if I took the gate voltage away? No way. Everything's set. This guy's turned on. There's that negative. There's that negative. That sucker's on, and it is on. It is on. How do you turn it off? Reverse bias it. So in AC, it's no problem. AC, it would automatically turn off on the next alternation. Y'all understand that? So as soon as it goes back to 0, so what we do, and this is called, we say firing, we fire SCRs. So what we do is we don't put a positive, a constant positive on the gate, we put a pulse. We fire it, and then it turns on. Stays on for the rest of the alternation. When it gets down below the holding current, which is going to be less because we got about 2.1 volts right here, right? So as soon as it gets down below that, there can't be any current flow through it. If there's no current flow through it, then what will it do? It'll cut off. And then we wait on what? We wait in the next alternation. But what we can do, if they show this, so we're going to have 3 leads on these things. And what you got to do to bias it, you have to make the gate positive in respect to the cathode. So if I'm going to make it positive in respect to the cathode, then normally we're going to have to, we might have a lead coming on the cathode too. But we're definitely going to have 3 leads coming off of it. So these are different SCRs. This guy right here looks like a transistor, but it's not. So just because a device has 3 leads on it, don't say that's a transistor. Right now we know it could be a BJT or it could be an FET, and now it could be a what? Could be an SCR. Then we have all these packages, and what determines the size? What determines the size of a transistor? What determines the size of a water valve? The amount of water has got to flow, right? So what determines the size of the SCR? How much current we're going to try to push through that thing? What determines the size of a diode? How much current you're going to push through it, right? So it's just like these guys are valves. But what's nice about this guy is we can either do what? Turn it on. And then it's got to, somehow we've got to turn it off. And we'll find out later on we can turn it off. So these guys, we use these on DC sometimes, but we got to figure out a way without it. Now AC will automatically do what? Turn them off. But DC, if I leave DC on them and don't do something, these guys, once they're on, they're going to be what? They're going to be on. So this is the VI characteristic curve for an SCR. This is the breakover voltage right here. And this is the reverse breakover voltage. If you exceed the reverse breakover voltage, what's it going to do? Huh? If you exceed the reverse breakover voltage, what's going to happen? Yeah. We had a there was we called it the pollution pond, but it was the place where they actually pumped a lot of the sewage out at US Steel. It was down at the very end down there, and they had the big old pumps they used were wound rotor motors. A wound rotor motor is it's hard to explain, but what you do is to change the speed of the motor, you change the resistance of the rotor, so it has slip rings coming out. But also, if you take output off the rotor, it's also a generator. So the way they adjust the speed is they put SCRs in the armature circuit, which is really neat. And what they would do is it was all in phase, and they would feed the energy off the wound rotor motors back into the power grid. It was really, really neat. And man, we had one of those guys blow up one day, and that whole cabinet just shook. It's lucky we didn't have it open, but you couldn't run it with the cabinet open. By the way, if you exceed this forward voltage right here, the SCR turns on. But So we don't want to put more voltage to break it over forward bias. If you break it over forward bias, it's not going to damage it. It's just going to do what? It's going to turn on. And we've lost control of the SCR. So we don't want to get too much voltage on it to break it over forward bias, because if you break it over forward bias, it's going to turn on. If you break it over reverse bias, then you're pushing voltage to you're pushing a lot of current through a voltage, and it's going to burn it up. Everybody understand that? So what we do is it's going to block all the voltage. This right here is representing a little bit of leakage current. So this represents a little bit of leakage current until we do what? Now, until we break it over. Or until we fire it. Well, you have to drop it below its holding current. So once these guys are turned on, you have to drop it below its holding current. I don't know. I'd have to think about that. Let me bring up another PowerPoint, one that's white, because I can't draw on that. So what we have the ability to do, let's look at a half-wave rectifier. So normally in a regular circuit, I'm bringing AC in, and then of course over here, if I ran this through a diode, then I would get, let's turn it the other way, then I would get this out, right? Everybody okay? And then my average voltage would be V peak over pi, right? If I come over and change this to an SCR, then what I can do is I can delay the firing. So let's say we wait till this input voltage gets up to there before we fire it. Then what we'd end up getting out is we'd end up getting this. And it would finish out the cycle, and then I'm firing it right about here. So it's going to go vertical here, and we're going to do what? And we're going to finish out the cycle, and then we're going to drop down. So that means if this is V peak over pi, then what would that be? Is it going to be more, or is it going to be less? So you're saying this would give me a higher average than this? So what we're doing, let's just draw one alternation. And let's say on my input signal, I'm firing right there. Well, what my DC would do, it would come over, my output would do, it would come over there, it would go vertical right here, then it would come over here and it would finish the alternation. So this right here would give me less, which means my motor will run slower. Right, you understand that? If we come over here and fire it right there, then all I'm getting out is I'm getting out this much of the alternation. Would the motor run slower, or would it run faster? So I'm getting this. Okay, now I'm getting this. So you're saying my DC motor would run faster with this than it would with this? Yeah, so what we're saying is if I delay the firing of the SCR, the motor would slow down. Right? You understand that? Yes or no? So if I fired it right off the bat, it would run at full speed. It would see V peak over pi. But as I move this thing over, it's going to start slowing down. By the way, we refer to this as a firing angle. Everybody knows that a sine wave, so how many degrees would that be? One alternation of an input. I know that's not pretty. So how many degrees in a cycle? Okay, 360. How many degrees in an alternation? 180. Now what we do is we refer to as what we call a firing angle. Okay. So if I fired it right here, then I'd get this on the output, and we'd say that would be about 45 degrees. A firing angle of 45 degrees. Everybody understand that? But what if I came over here and did this? Let's say I come over here. We can connect these gates together, by the way. We can fire it off the same circuit because one of them's going to be reverse biased. Only one of them's going to be forward biased. So we can gate this guy right here at the same time we gate that one. But if this is positive, this right here is going to be what? Negative. And even though I gate them at the same time, this guy here would still be off because it's what? It's reverse bias. So what we would get on the output right here is if I turned them on instantly, we would get this. Right? You understand that? If I delayed the firing, let's say we delayed it by 45 degrees, then what I'd get out is I would get this, right? So my DC motor, it don't care about this. All it sees is the averages anyway. My DC motor would come in and run slow. So look on your formula sheet where we can calculate the average voltages. Should be on there somewhere. I think it's on the back. Should be a section on SCRs. So DC out or DC average is equal to what? What does it say? I'd have to go look. I know it's times like the sine of the angle or something like that. I know it's this is full wave. Y'all see something on there? Is it on there? On the average output voltage? Yeah, this full wave says V peak over pi. It don't say 2 V peak. Huh? V peak over pi. Cosine. Huh? Is that it? Okay, I'm sorry. It's a little more than I thought it was. I remember. I guess I need to look at the formula sheet. Am I going to run out of room? Does it go on out here? So, okay. Then we close this here, huh? We close this one. Oh, open another set. Oh, okay. We open another set like this. Times the 1 plus cosine, open parentheses, alpha times, close the parentheses again, right here. Okay. What comes next? Close it again?
Yeah.
Okay.
All that.
Divided by what?
Yeah.
So what was it? What would full weight be? Same thing, but it'd be without the 2. I'd have to go back and figure out what the alpha is. I know what the alpha on a transistor is. The cosine would be the cosine of the firing angle, right? Right? Yes. Yeah. Huh?
Yeah. I paid.
Oh, okay. The angle theta. Yeah. Okay. Times the cosine of the angles. What it is? Like, yeah, that's it. So as the angle goes up, the cosine goes down, which means our average voltage would go down, right? So, but these guys here would automatically turn off. Now we can also come up and see it like this too. This is very popular because here requires a center tap transformer. So if you see it in a full wave, and I would have to look up the 3-phase. What we do is we'd make these two right here SCRs. Normally we connect the gates together. We can connect the gates together because one of them's reverse bias. These two right here would be regular diodes because they only serve as the return path. So you only have to have 2 SCRs. And then we'd bring our AC in right here. Now if it's 3-phase, then what we would do is we'd come over here and we would add a 3rd SCR and bring in the 3rd phase, which I've run out of space, guys. We'd bring in another phase into here. And then this would be 3-phase. This is predominantly the type of drive you'll run into in industry because 3-phase gives you a really good DC output without having filters. And this would be a three-phase SCR. We used to call, out of US Steel, they called them buckets. Let's say a 3-phase bucket. And then they'd use 2 buckets. They'd hook them back to back. And this guy here was turned in the opposite direction. And this way what they could do is they could run the motor either forward or reverse. So that, and this right here was connected together. So what they could do is they could either run the motor what? Forward or reverse just by turning on one bucket or the other bucket. So AC, we've got no problem because AC automatically. Now, what's the advantage of an SCR over a transistor? So I could control the speed of a DC motor with a transistor. Or I could control the speed of a DC motor with a rheostat. So why is this the most popular way of controlling a DC motor? Yeah, because these things are either on or they're off. These guys right here to control the speed would have to put that sucker in the what? In the active region. When it's in the active region, it's dropping a voltage collector to emitter. If I put current through a voltage, it's going to create a lot of heat. Y'all understand that? These guys right here are either on or they're what? Off. When they're on, they're going to drop about 2 volts, right? When they're off, they're going to drop the entire voltage. So this is why these are the predominant method of driving DC drives, driving motors. Now, to control it is very, very complicated. We're going to do a very, very simple circuit. So what we'll do is we'll come in with AC. We'll come off the transformer. will come into a diode. And then we're going to come in and we're going to run it through a resistor. No, we want to do it that way. Hold on a second. So we'll do a half wave. Very simple. So I'm going to come over here and run this through a diode. Oops, that ain't going to work, Rich. I'll get it in a minute, guys. Just bear with me. Put a diode right here. Then I'm going to put a resistor. And then I'm going to put a capacitor. This right here will make this a variable resistor. I'm going to come over here and we're going to run a little motor. And then we're going to use a permanent magnet motor. And then we'll put an SCR right here. And we'll take our gate and connect it right there. And this is going to be a permanent magnet DC motor. Y'all understand those? You're okay there? This represents the commutator on the DC motor. So how's this guy right here going to work? So we're going to use a small motor, half wave. So we're not going to get a full wave out of this guy. So what we're doing up here, and y'all guys have had AC, is we're setting up an RC time constant. So depending on this guy right here, how high you set this, depends on when this voltage gets up high enough to trigger the SCR. So the more time we add, the bigger we make this resistor, the more this SCR is. So on the SCR, we're putting this on it. If we set this to 0, then the SCR is going to fire almost instantly, and we'll get this right here out. When I come over here and add more resistance, then what's going to happen is we're going to delay when we get enough gate current to fire the thing. Does that make sense? Which means it's going to start doing what? It's going to start moving over here. Our motor should do what? Should start slowing down. Now with this circuit, the best we can do is 90 degrees. Because as soon as I go over that, my capacitor, my thing will never charge up again, right? In other words, my time constant will be too long and we won't be able to charge that. So an SCR firing circuit is very, very complicated. It's an electronic circuit. This will be the only little circuit that we'll see just to play around with. And we'll control the speed of that motor. We can control it down to 0 up until 50%. And I think this is the lab we'll hook up. And there's another lab that we'll look up. The book talks about how to run this thing in a DC circuit, which is really, really interesting. So a lot of your golf carts out there use SCRs. Well, golf carts run off of batteries. But we need something, but we don't want to run the speed of the motor through a transistor, right? You understand? We don't want to run it through a resistor. We don't want to run it through something that's either on or off and can handle a lot of current. But the problem is if I have DC batteries out there and I turn on an SCR, then I would be in for a ride unless I came up with some way we could turn it off in a DC circuit. And I think the book does a really good job on this. This is the first circuit I ever seen. The SCR is turned on by applying a pulse of control current to the gate. And we refer to that, by the way, as firing. We say firing the SCR. Once turned on, the SCR remains on as long as there is a minimum level of holding current flowing through the circuit or through the SCR. This says through the load circuit, but it's through the SCR. Y'all understand that? Where do we find the holding current at? In the data sheets. SCRs can be turned on. SCRs can be turned on by damaging methods such as voltage breakover turn on, static turn on, or thermal turn on, which means we get them too hot. Are we okay? The internal structure of the SCR consists of two PN junctions joined together to form a PN-PN layer. And I said it has 3 junctions. It's actually got 3 layers, right? 4 layers. Reverse bias voltage is applied to the layer structure. There is no noticeable current flow due to the formation of the depletion regions. Everybody okay there? Book does a really good job on this. With forward bias voltage applied to the layered structure, there is no noticeable current flow due to the formation of the larger depletion region in the center. Everybody understand that? When the SCR is pulsed or fired or triggered, a forward bias applied to the cathode and anode, the SCR conducts. The current continues to flow as long as this current is supplied. How long will it flow? Until we drop it below. Somehow we drop it below its what? Below its what? Holding current. They use this equivalent circuits a lot to teach SCRs, but an SCR cannot be this because the main current flow would be through the base of this guy right here. But if you did a transistor like this, it would latch on. It's a cute little circuit, but an SCR can't be like that because this guy wouldn't handle a lot of current. So this is one way you can make a latch with bipolar transistors. So this is a circuit they're looking at. So notice we have 2 push buttons. Yeah. So this guy right here, I'm sorry, where's the gate at? This guy right here would do what? Here would do what? And then this guy right here would short it out, which would do what? It would turn it off, right? Oh yeah, this is what I didn't see, the gate buttons. So this is one way we can turn it off. So if we came with some method where we could just short it out momentarily, right? You understand? Here they're using a push button. Then what would happen to my current? The current would go around here and the SCR would turn off. I wouldn't want to be pushing that button though on that 600 amp monster over there. Here's another method that we could do. This is the method that we use. So this would be pretty much the same method that you use in a golf cart. And what they do is we have an electronic circuit that fires these things like this. So what they're doing is they're applying pulses, right? You understand that? And then they can control the pulse width, which would control the speed. I think in this class I showed y'all that pulse width modulation, right? So that's what they're doing right here. But what we're doing is this little guy over here is going to turn it off. This is going to be the main guy. So the way this thing works is I'm going to turn it on. This button right here is not pressed. So what's going to happen is this capacitor, this is going to charge up negative. This is going to charge up positive. You understand that? Now what's going to happen when we press that button relative to ground, this is going to come over here and it's going to place that positive on the capacitor on that side. What do we got this guy charged up over here? Negative. And what's the guy going to do? It's going to cut off. And how long is it going to be off? Until I press this button right there. And it's going to stay on. I don't hold it down. I just do what? Touch it. Charges this capacitor up, negative to positive. Y'all see what I'm saying? Then when I fire this, that effectively takes this positive, flips it over there for a heartbeat, SCR turns off. Now if I can control this electronically, then what can I do? Then I can use this to change the pulse width, which would change the speed of this motor. So this is the one, this is a very popular circuit we use to use DC, use SCRs in a DC circuit. They call that a commutating diode, by the way, which is kind of strange. When S1 is closed, the gate current flows through the SCR and resistor R2, turning on SCR1. This in turn allows current to flow through the load, turning on SCR1, also grounds the left side, and they're going to go on through here. When a charged capacitor of opposite polarity is applied across the SCR will stop conducting. The polarity of the voltage across the capacitor reverse biases the SCR, so the forward current of the SCR drops below holding level and stops conducting. So that's what we're doing. When we fire that other SCR, we're doing this. So this guy's charged positive on this side, negative on that side. Can y'all see that? During the positive half cycle, SCR is forward biased. So we're going to kind of go through this. What are we doing here? Oh, this is the circuit that we just looked at. So what they're doing in our circuit, so here's our diode. Here's our RC time constant. Looks like what they're doing in their example is tapping off different places. What we'll do is we'll actually put a pot wired as a rheostat right there. And we should be able to control it, right? We got some SCR firing circuits. They're very, very complicated. We used to teach a class in process controls where what you do is you come up and create a circuit that creates a ramp. And then the ramp is in phase with, so this would be in phase with one of these. This would be in phase in one of these. And then what you do is you trigger this thing to fire on this ramp. Does that make sense? And then in that way we can control the firing angle anywhere from any location along this. We can control the firing angle, and we can really, really control that. So an SCR is very, very complicated. There are some schematics on the line. They're very hard to obtain. This is one of those things that are proprietary, so most of your big SCR control package, people don't give schematics out on those things. And there's a lot to it too, because especially if you're controlling a big old 200 horsepower motor, you got a lot of safety built into it, whether if it stalls, whether if it overcurrents or all kind of stuff. There's all type of sense circuits in there. But it's basically just generating some type of watt. So we generate some type of ramp that's in phase with the input signal, and then what we do is we set up a circuit that we can fire it anywhere along that ramp, and then then it would reset and generate another ramp. We could do a circuit, but we're not going to do that. So SCRs are really, really neat. Normally we find them in DC drive circuits, driving DC motors. We have to fire them to turn them on. But to turn them on, they have to be forward biased, right? You understand, which means the anode has to be positive in respect to the cathode. We have to fire it. We have to make the the gate positive in respect to the what? In respect to the cathode. Once it's turned on, how do we turn it off? We didn't even short it out a while ago. That's one method. We drop it below its holding current. Now, there's different methods we could do it, The method they show in the book, we are not shorting it out. What are we doing? We're reverse biasing to a capacitor. Capacitor discharges instantly, but there's no current flow through the capacitor, right? Y'all understand that?
They did a first one, they had a switch, they had push with, they had a pass on that.
You could, but you'd have to hold the push button down the whole time if you want it, and when you let it go. So yeah, that was a push button. You could run a motor, but you know, odds are it's going to have a lot of control in it. And like I said, the bigger the industry and the bigger the motor, the more safety you're going to have built into the drive circuit. What we'll do next class is we'll come in and we'll look at we'll see if I can find some drive circuits on there and show you the complicated and how we fire these things too. Normally, and I know it's time to go, guys, but it's normally on our SCR, the higher the voltage. What advantage does high voltage have over low voltage? Huh? What advantage does high voltage have over low voltage? I mean, what advantage does high voltage have over low voltage? Yeah, you just can't say lower current. It's lower current to produce the power, right? You understand that? So the higher the voltage is, the less current it's going to take to produce power. Okay. What advantage does low voltage have over high voltage? Safe. So if I'm going to run a 300 horsepower motor, you think we're going to run it off 50 volts? No, we're going to run it off 700-800 volts, right? You understand? Am I going to bring 708 volts into my cabinet? No. So what we'll do later on is show you how we fire these SCRs. What we would like to do is we'd like our electronics to be running at real low voltage, right? And then somehow we're going to have to fire this sucker and make it positive in respect to this voltage out here. So what we'll look at next time is what you'll run into, how we actually fire these things. High voltage firing circuit. Low voltage. How can a low voltage circuit be isolated from a high voltage circuit and still fire these things? And that's pretty interesting. Y'all have a good one.